Let's say I have two continuous functions, function f and function g. And let's say I wanted to find the area between those two curves on some closed interval between a and b. Let me shade in what that area would look like. Let me tell you the rule we could use to find that area, and then I'll explain to you why that rule works. So these functions f and g are continuous on the closed interval ab. And notice that f at x is greater than or equal to g at x for all x on that interval. So if those two conditions are met, I know that the area between f and g on that interval is equal to the definite integral from a to b of f at x minus g of x dx. Let me explain to you why that definite integral will get us that area. So let me zoom in on this diagram a little bit. And remember, the area under a curve, or in this case bounded between two curves, we could start to think of finding that area using the limit of a Riemann sum. And remember, the idea behind a Riemann sum is that we try and fill this with an infinite number of rectangles and let the width of those rectangles approach zero. Instead of trying to draw a bunch of rectangles inside that area, I'm just going to draw one rectangle as a representative rectangle to be able to explain to you what's going on here. So I'm going to just pick this x value right here. I'll call it x sub I, and I'll use function g and function f at that x value to be able to figure out how to draw the rectangle. So this point right here is x sub I, g at x sub I. And up top on function f, I've got x sub I, f at x sub I. And now let me draw my rectangle, where function g tells me where the bottom of the rectangle should be, and function f tells me where the top of the rectangle should be. Now you have to imagine me finding the area of this rectangle and infinitely more rectangles that fit underneath this curve, and more importantly, the width of those rectangles is going to be approaching zero. Well, how would I find the area of just this rectangle? Let's start with that. Well, the width of this rectangle, we'll just call that delta x. So the width of this rectangle is delta x. But what is the height of this rectangle? Well, we could calculate that. The height would just be the vertical distance between that point and that point. So I would just subtract that y value minus that y value. Always the top one minus the bottom one so that we get a positive height for this rectangle. So I would just do f at x sub I minus g at x sub I. And then to find the area, we would just find the limit as the number of rectangles under this curve approaches infinity of the sum of the areas of all these rectangles from rectangle 1 up to rectangle infinity. And the area of each of those rectangles we would get by doing the rectangle's height, which I just told you is f at x sub I minus g at x sub I times the rectangle's width, which I said we'll call it delta x. So once again, we just have height times width. And we're going to add all the areas together, and we're going to have an infinite number of rectangles. We know that we can rewrite this limit of a Riemann sum. We can rewrite it as a definite integral. So I could rewrite that whole limit. I could rewrite it as a definite integral from a to b of the height of the rectangle, which I told you we'll do f at x minus g at x to get the height of that rectangle, times the width of the rectangle, which in integral notation we use dx to represent the width of the rectangles, and that implies we're letting the width approach 0. So in this notation, we still just have height times width. And notice that formula is the exact formula that I wrote here for you. And no matter where the two functions are, whether they're both above the x-axis or both below or one above, one below, it wouldn't matter, as long as on the interval from a to b, f at x is above g at x, then f at x minus g at x is going to give us the height of the rectangle. Right? Finding the difference in the y-coordinates is always going to give us the height. So let's practice using this formula to find some areas between curves. Example 1 says find the area of the region bounded by the graphs of y equals x squared plus 2. Oh, I can tell that's the red function. I'll call this one function f at x. So there's f at x. Y equals negative x, which I can tell is the blue function. I will call that g at x. So here's function g at x. And x equals 0 and x equals 1. Those are my two vertical lines that are the left and right boundaries for my area. So if I want the area between f at x and g at x, well, on that interval, f at x is always above g at x. So I can just find the area by doing the definite integral from 0 to 1 of f at x minus g at x dx. So let's come up with a formula for f at x minus g at x. It would be x squared plus 2 minus negative x dx. Let me simplify that a little bit. So I have x squared plus x plus 2 times dx. And now based on the fundamental theorem of calculus, I know I can evaluate that definite integral by finding the antiderivative of my integrand, evaluating it at 1, and then subtracting its value at 0. So the antiderivative of x squared plus x plus 2 would be x cubed over 3 plus x squared over 2 plus 2x. So I want to find that function's value at 1 and then subtract that function's value at 0. So this would give me a third plus a half plus 2 minus the antiderivative at 0 is 0 plus 0 plus 0. And if I add those together, I get 17 over 6, which is about 2.83. So this area right here is 2.83 units squared. Let's try another one. Find the area of the region bounded by the graphs of f at x equals 2 minus x squared. Well, I can tell that is the red function. And g at x equals x. There's my linear function. It is in blue. Now this time my left and right boundaries for my area are unclear. I don't know what my a and my b values are, so I don't know my lower and upper limits of integration. I'm going to have to start by finding those, by finding where do these functions intersect. Let's find these 2 points of intersection so I know my boundaries of integration. So I'll start by finding the points of intersection for these two functions. So I'll set them equal to each other. And then I'll solve. Well, it's a quadratic, so I'll set the quadratic to 0, x squared plus x minus 2. And this quadratic has rational answers, so I can solve it by factoring. Multiplies to negative 2 and adds to 1 are 2 and negative 1. So the solutions to this are negative 2 and 1. So I just figured out my a value is negative 2, my b value is 1. So I can now find the area using my definite integral. It would be the integral from negative 2 to 1 of what function is on top on this interval. F at x is on top over that entire interval between a and b. So it would still be f at x minus g of x dx. Let's get an expression for f at x minus g of x. So I've got my f at x function, 2 minus x squared. I have to subtract the g at x function, which is just x. And now I will want to find the antiderivative of that integrand, which would be 2x minus x cubed over 3 minus x squared over 2. And I'm going to rewrite my limits of integration as negative 2 and 1. And now I just have to evaluate that function at 1 and then subtract its value when x is negative 2. At an x value of 1, the antiderivative has a value of 2 minus a third minus a half. And then I have to subtract the value of the antiderivative when x is negative 2. So that would be negative 4 plus 8 thirds minus 2. And that gives me 9 over 2, which is equal to 4.5. So I know the area between the curves on that interval is 4.5 units squared. Let's do another example where the functions intersect at more than one point. Find the area of the region bounded by the graphs of f at x equals 3x cubed minus x squared minus 10x, and the quadratic negative x squared plus 2x. Well, my blue function is quadratic, so I know that it must be g at x. And the red function is the cubic function, so I'll name that f at x. If I want the area, I'm actually going to have to find all 3 points where these functions intersect. Of course, we need the first and last point of intersection so that we can find our limits of integration, which I've been calling a and b. But why do we care about this one right here? Well, notice before that point, so from a to 0, function f at x is above g at x. But then from 0 to b, function g at x is above f at x. So when I'm calculating this area, I'm going to have to use two separate integrals. I'm going to have to do the integral from a to 0 of the top function minus the bottom function, so f at x minus g of x dx. And then to that, I'm going to have to add the definite integral from 0 to b, but this time of g at x minus f at x, because we always have to do the top function minus the bottom function. So we're going to have to find those a and b values, and I'm guessing that middle one is at an x value of 0. It sure looks like it. Maybe it's just really close. We'll see when I find the points of intersection of these two functions. So let's start by finding the POIs. I'll set the functions equal to each other. I'll rearrange to set it equal to 0. And then I'll solve this by factoring. I'll common factor a 3x. And then I see I've got a difference of squares. So I've got 3x, x minus 2, x plus 2. So my zeros of this function are negative 2, 0, and 2. So I know the a value is at negative 2. This value right here is at 0, and the b value is at 2. So now in my area calculation, I can replace a and b with what I know they're equal to. My first integral is from negative 2 to 0, and my second integral is from 0 to 2. And now it's just a matter of plugging in our functions, calculating some antiderivatives, and then we'll have our area. So I'll start by subbing in my functions. F at x minus g at x would be 3x cubed minus x squared minus 10x minus negative x squared plus 2x. And g at x minus f at x would be negative x squared plus 2x minus 3x cubed minus x squared minus 10x dx. Before I do any antiderivatives, let me start by simplifying those integrands. And now I will find the antiderivative of each of those integrands. So the first one would be 3x to the 4 over 4 minus 12x squared over 2, which I'll just write as 6x squared. And then my second definite integral, the antiderivative would be negative 3x to the 4 over 4 plus 12x squared over 2, which I'll just write as 6x squared. And now I'll do this in two parts. The first part I'll do in blue. I need to find the value of that antiderivative at 0, which is just 0, and then subtract the value of that antiderivative at an x value of negative 2, which would be 12 minus 24. And then the next one I will do in orange. I need to find the value of that antiderivative when x is 2, which would be negative 12 plus 24, and then subtract the value of that antiderivative when x is 0, which is 0. So let me just move this over a bit. And this is equal to, well, the area of my first definite integral, 0 minus negative 12, that's 12. So I know that this first area is equal to 12 units squared. And my second area, in orange, I see negative 12 plus 24 take away 0. That is also 12. So the second area right here, I guess, is also 12 units squared. So my total area bounded by those two curves is 24 units squared. Let's do one last example. Example 4, we're going to do a little bit differently. It says to find the area of the region bounded by the graphs of x equals 3y squared and x equals y plus 1 squared. So notice these are both functions of y. X equals y plus 1, well, that's the linear function. So that's the one in blue. It's a function of y. So I'll call that one g at y. And that's in blue, so here's g at y. And this function here, x equals 3 minus y squared, that is also a function of y because x is isolated, so I'll call that f at y. It's actually going to be easier because x is isolated. Instead of using x values for my limits of integration, I will actually use y values for my limits of integration. If I can find the y value of this point, I'll call that a, and the y value of this point, I'll call that b. I can actually find this shaded area by doing the definite integral between a and b of f at y minus g at y dy. Now, why is this definite integral going to work? Let me draw a representative rectangle inside my shaded area here at some y value. I'll just pick this y value right here. And I will use the value of g at y and f at y to guide my drawing of that rectangle. And let me actually label these 2 points I use. The red function, remember, is f at y. So this point is the point f at y, y. Remember, the function calculates the x value based on the y value. And this point over here is the point g at y, y. Now, if I were to find the dimensions of this rectangle, let me think of this as the width of the rectangle. How could I calculate the width of that rectangle? I would just find the difference in the x values. I would do the bigger x value minus the smaller x value. So I would do f at y minus g at y. And then the height of the rectangle, we could just call delta y. And delta y is what we would want to be approaching 0 if we wanted to fill this with an infinite number of rectangles. And that's exactly what this notation says. We've got the width of the rectangle times the height. And this dy notation paired with the integral tells me that we're letting that change in height approach 0. So let's use that formula to calculate the area. But before I can do that, I guess I have to get the a and b values, my limits of integration. So where do these functions intersect? So let's find out where are the points of intersection of these functions by once again setting them equal to each other. So it's a quadratic relationship, so I'll set it to 0. And this would factor to y plus 2, y minus 1. So I have two y values. They intersect at a y value of negative 2 and at a y value of 1. So my a value is negative 2. My b value is equal to 1. So when I use my area formula, my limits of integration are between negative 2 and 1. And I can sub in my f at y and g at y equations. So f at y is 3 minus y squared, and I have to subtract g at y, which is y plus 1 dy. If I simplify this, I've got negative y squared minus y plus 2. And now I need to find the antiderivative of that integrand. That would be negative y cubed over 3 minus y squared over 2 plus 2y. And we want this at y values of negative 2 and 1. I'll evaluate the antiderivative at 1 and then subtract the value of the antiderivative at negative 2. So at 1, I've got negative a third minus a half plus 2. And I want to subtract the value of that antiderivative when x is negative 2. That would give me 8 thirds minus 2 minus 4. And that gives me 4.5 units squared. So that shaded area there is 4.5 units squared. Jensen Math!